In the last video, we looked at solving systems of equations, linear equations particularly, meaning that we were looking for if and where two lines cross, meaning they share a point, and we looked at that visually using the graph. This video is going to focus on how I can find the point of intersection, the point that the two graphs share, algebraically. We're going to learn two different methods to start. And the first one called the substitution method. Substitution, kind of like having a substitute teacher, means putting something in place for another. So when I'm out sick or I'm not in school, I have a person who takes my place as teacher. So we're going to do something similar algebraically. So before, when we were looking at these graphically, if I had a system, I would have solved both the equations for y and graphed them. The problem with graphing is if my solutions are either extremely large values for x and y or we get weird fractions, that's hard for me to determine using a graph. So algebraically I can solve for them without having a picture. So in substitution, what I'm going to do is I'm going to pick one of the two equations and solve it for one of the variables. So when I look at them, I'm going to choose which equation and which variable would be easiest to solve for. I see that in example 1, in the second equation, the x is already by itself. There's no number in front of it. So I'm going to solve that equation so that it says x equals. I'm going to do that by subtracting 3y from both sides to get x equals 3 minus 3y. So now, what that means is in the other equation, wherever I see an x, then I can replace it with 3 minus 3y. That equal sign, x equals 3 minus 3y, means they are equivalent and can substitute each other. So I can then say that I have 2 times replace the x with the 3 minus 3y, and now you'll notice that the equation has only y's in it. So I'm going to use my distributive property and carry that 2 through, so that I have 6 minus 6y and then plus 5y equals negative 5. So I'm going to solve for y at this point. I've got negative 6y plus 5y gives me negative y, and I'm going to subtract the 6 from both sides. So I get negative y equals negative 11, dividing by negative 1 to get y equals 11. So now that I have y equals 11, I can plug back in to the x equals or one of the two original equations. It doesn't matter what you choose, but since I already solved this one for x, I'm going to use that. So I'm going to say x equals 3 minus 3 times, and since it's a y, I can replace the y with 11. That, aka, that is 3 minus 33. 3 minus 33 is negative 30. So my point of intersection, my solution, the place where the lines cross, is at x equals negative 30, 11. So that would have taken me a bit in order to be able to actually see where these two lines cross. So algebraically made more sense to solve for this one. All right, let's look at the second one. So again, we're going to use substitution. Notice the second equation is already solved for y. So I actually don't have to solve anything for one of the variables. It's done for me, so I'm going to plug it in for y in the top equation. So I have 2x plus 5 times negative 2 over 5x plus 3, and that's supposed to equal 15. So I'm going to carry this 5 through. Treat it as 5 over 1 if you need to. So I've got 2x, 5 times negative 2 is negative 10 over 5x, and then 5 times 3 is 15. If you had done all of that in your head and said that that's just negative 2x, that's fine. So I've got 2x minus 2x plus 15 is equal to 15. What I notice here is, unlike the one before it where I got out y equals 11, my x's in this case cancel out. 2x minus 2x is 0, and I'm left with 15 equals 15. This is a true statement. 15 does in fact equal 15. It always will equal 15. So since this comes out as true, what this tells you is that there is an infinite number of solutions. This is the example in the last video where when I solved the two equations for y, I got the exact same equation out. This means that they are the same line. Okay, so if you get a true statement, 15 equals 15, 0 equals 0, negative 5 equals negative 5, something along those lines, that means that the two equations are the same, so you have infinite solutions. If you get out something simply that x is negative 30, y is 11, you have one solution, meaning the two lines in the graph cross one time. Let's look at the third example. So neither of these have a variable that is just by itself, so we need to pick and solve for one of the variables. I'm just going to go ahead and take the top one and solve it for x. So I'm going to take away the 5y from both sides, so I have 9 minus 5y, and then divide both sides by 3. So that leaves me with x equals 3 minus 5 over 3y. So I can take this and plug it in for x in the second equation. So I've got 9 times 3 minus 5 over 3y plus 15y is equal to negative 2. When I carry this 9 through, I get 27 minus 9 times negative 5. If I treat it as 9 over 1, I get negative 45 over 3. Negative 45 over 3 is 15. So I get minus 15y plus 15y equals negative 2. Similar to the last one, the variable pieces cancel out. But this time, instead of a true statement, I get 27 equals negative 2. That is not a true statement. So what this tells you is that there is no values for which these two graphs cross. So I have no solution because they are parallel lines. They never cross. Now this would be a good example of one where if I didn't want to have to try to solve for one of the variables, I can use the next method, the elimination method. So in the elimination method, I can multiply one or both equations so that one of the values, either the x's, the number in front of the x's, or the number in front of the y's, become the same value. So if I take a look at example 1, I notice that if I multiply the top equation by 2, I can get the 3x to be a 6x. It doesn't matter about the rest of them, I just want one of the variables to be the same. So if I multiply the 3x by 2, I have to multiply the entire thing by 2. And then I get 6x minus 14y equals 20. And I'm just going to pull over the other equation. I didn't do anything to it. So now what I'm going to do is I'm going to decide whether I'm going to add or subtract the equations so that the x's eliminate. We want one of the variables to eliminate. In this case, it's going to be the x. I see that if I subtract them, the x's will cancel out. 6x minus 6x is 0. Negative 14 minus negative 8 is negative 14 plus 8, which gives me negative 6. Okay, so I get negative 6y. 20 minus 8 is 12. If I divide both sides by negative 6, I get y equals negative 2. So now I'm going to take this y equals negative 2 and plug it back into one of the two original equations. It doesn't matter which one. I'm just going to use the top just because it's the top one. So I have 3x minus 7 times negative 2 is equal to 10, and I'm going to solve. So I've got 3x plus 14 equals 10. Subtract 14 from both sides. 10 minus 14 is negative 4, and then I'm going to divide by 3. So in this case, my solution, this means the graph crosses at one place, is x equals negative 4/3, comma, negative 2. Be careful that you write the ordered pair as x, comma, y. Let's look at example 2. Okay, so again, I see in this case, if I multiply the top one by 10, I can get the numbers in front of the y's to be the same. So I'm going to multiply by 10. That's going to give me 10 times 3 is 30, divided by 5 is 6. So I get 6x. 10 times negative 2y gives me negative 20y, and 1 times 10 is 10. And then just pull over. Okay, so in order to get the y's to cancel, I see that I can subtract. I also notice that technically both of these are the same equation, but let's go ahead and do exactly the same steps as we did last time. 6x minus 6x is 0. Negative 20y minus a negative 20y is the same as negative 20y plus 20y. That's 0. And then I get 10 minus 10 is 0. So I get 0 equals 0. This, unlike in the past, this is a true statement, not a false statement. So always true means infinite solutions. And we saw already up here that it's the same line. Let's do one more example together. Okay. So I see in this one that there's not one value that I can multiply just one equation by in order to get the other to cancel out. So I'm going to choose to get rid of the x's, and I'm going to multiply both equations by something. So I'm just going to take whatever number is in front of the top one and multiply that to the bottom one, and whatever's in front of the bottom one I'm going to multiply by the top one. So 7 times 1/4 gives me 7 over 4x. 7 times negative 2 over 7 gives me negative 2y, and 7 times 1 is 7. And then I'm going to do the same thing on the bottom. 1/4 times 7 is 7 over 4x. 1/4 times negative 8 gives me negative 2y, and 12 times 1/4 is 3. So again, I choose, am I going to add or subtract to get the x's to cancel out? So I'm going to subtract in this case, since 7/4 minus 7/4 gives me 0 to get the x's to eliminate. Then I get negative 2 minus negative 2, so negative 2 plus 2. So I get 0 equals 7 minus 3 is 4. This is not a true statement, so we have no solution. If I have no solution, that means I have parallel lines. They never cross. So for class next time, I want you to do, on the last page you have 10 examples to try. I want you to do numbers 2, 4, 6, and 8. It does not specify which method to use, so what I want you to do is substitution for 2 and 4 and elimination for 6 and 8.